In this experiment, we have used an optical sensing interrogator to measure the strain of an object. In industry, this can be used to measure the strain of various parts of a structure.
In this laboratory experiment, we will be investigating the strain of an aluminum beam under various loads and the strain as its temperature is changed. Strain is a measure of the deformation of an object. It is defined as the change in length per unit length. As such, it is technically dimensionless. In this experiment, we will be working in units of microstrain, which is the change in length in micrometers per unit meter. When a beam is placed under load, the top is put into compression. Similarly, the bottom is stretched. Additionally, as the temperature of the beam changes, the length will also change in accordance with the material's coefficient of thermal expansion.
The optical interrogator sends a beam of light down this fiber optic cable in a wavelength range of 1500 to 1600 nanometers. At the end of the cable is a fiber Bragg grating. The light will interfere constructively with this grating depending on the spacing, and the shift in wavelength is affected by the strain and the temperature. This is the strain sensor. It is comprised of a fiber Bragg grating. It is glued to the material being measured. Stretching and compression of the strain sensor changes the fiber Bragg grating spacing, and the wavelength reflected changes. In the thermal sensor, the index of refraction changes with temperature, and the wavelength shifts. As temperature contributes to strain measurement, we must use separate sensors to compensate for this and extract the stress due to mechanical strain.
Here, we have mounted a strain gauge to the bottom of a beam to measure how much the beam stretches when placed under load. At the same location, we have also placed a temperature probe to separate any temperature components to mechanical components of the strain. The beam is then placed across 2 points and put under loads in 100-gram increments.
This is the nLight software provided by Micron Optics to interface with their devices. In the Acquisition tab, we can observe the reflected signal for all attached sensors. The chart is intensity versus wavelength. The software will automatically detect and track peaks.
On the Sensors tab, each reflected peak can be given an ID. The wavelength of each peak can be translated into the physical parameters they represent. Here we see how the strain gauge translates a change in wavelength into the strain the sensor is under. On the Charts tab, the output from the sensors can be charted in real time. On the top, we have the output from our 2 temperature gauges, and on the bottom, we have the output from the strain gauge in real time.
Here's an example of how the experiment would proceed. As I add weights to the beam, the strain increases. And then I'll add one more weight. And you can see here that the strain jumps twice, once for each weight added.
In this video, we discussed the fiber Bragg grating experiment. We discussed the definition of strain, the difference between thermal and mechanical strain, how a fiber Bragg grating works, how to operate the Micron Optics software, and how to measure the strain of a beam under mechanical load.